Welcome to our exploration of machine learning, where we uncover a fundamental truth. Every decision, at its core, is a classification problem. Classification is the process that drives much of what we do in artificial intelligence. It involves taking an input, examining its features, and assigning it to the most probable predefined category. Think about everyday applications. Whether an algorithm identifies an animal in a photo, sorts spam from a legitimate email, or determines if a piece of fruit is ripe enough to sell, it's all classification. As you see in the simple diagram here, the input data, represented by the gray circle, is fed into a black box we call the classifier. The classifier's job, based on its training, is to sort that input. It must choose the most likely outcome from a set of possible categories. In this example, the input is sorted into one of three possible outcomes: Category A, Category B, or Category C, represented by the red circle, blue square, and yellow triangle respectively. This simple anatomy is the foundation of how we teach a machine to make complex decisions. To build a machine that can classify data, we typically use what's called supervised learning. This means we supervise the machine's learning process by giving it examples where we already know the correct answer. This process involves three key steps, using the example of classifying chicken eggs as fertilized or unfertilized. First, we establish the training set. This is the collection of data samples we want the machine to learn from. Each sample, in our case, an individual egg, is defined by its features. Features are the measurable attributes, such as the egg's weight and length. Second, we apply labels. This is the supervision part. We manually assign the correct class to each sample in the training set. This known correct answer is called the label. In this scenario, it's either fertilized or unfertilized. The machine uses these labels as the ground truth. Finally, we enter the training phase. The computer makes a prediction for each sample based on its current knowledge. It compares its prediction to the known true label. If the prediction is wrong, the system calculates the error, and we adjust the internal workings of the classifier accordingly. This iterative loop of predicting, checking the label, and adjusting the model is the core engine of how a system learns to become accurate. Let's dive into the simplest possible scenario: 2D binary classification. To visualize this, we use the egg data we just discussed. Since our data has two features, weight and length, we can plot each egg as a single point on a 2D plane. The vertical axis represents length, and the horizontal axis represents weight. As you can see, the fertilized eggs, marked by the red circles, tend to cluster in one area, likely characterized by certain combinations of weight and length. The unfertilized eggs, marked by the blue squares, cluster in a separate, distinct region. Since we have only two possible classes, fertilized or unfertilized, this is binary classification. If we want to build a simple classifier, we need to draw a metaphorical line in the sand to separate these two clusters. This line is known as the decision boundary. For this simple, well-separated data, a straight line works perfectly to distinguish the two classes. The true power of the decision boundary is that it doesn't just sit there separating the training data we used. It divides the entire two-dimensional space into distinct decision regions. Everything on one side of the line is permanently classified as fertilized, and everything on the other side is classified as unfertilized. This is the mechanism by which the classifier makes predictions on new, unseen data. If we introduce a new, unlabeled egg sample, a gray circle, for instance, the machine doesn't need to consult its entire training history. It simply checks which region the new sample's features place it in. If it falls into the red, fertilized region, it is classified as fertilized. If it falls into the blue, unfertilized region, it is classified as unfertilized. Notice the four charts here. The top right chart shows the clear separation into regions, and the bottom row illustrates how new, unknown data points are instantly classified based purely on which decision region they land in. The decision boundary turns an abstract space of measurements into two concrete classification worlds. While the linear decision boundary works perfectly for simple, well-behaved data, reality is rarely so neat. What happens when we introduce data from a different breed of chicken? Perhaps this new breed produces eggs that are heavier relative to their length, causing the groups to distribute differently on our 2D plane. As you can observe in this visualization, the red fertilized data points and the blue unfertilized data points are still distinct, but they are no longer separable by a simple straight line. If we attempted to use a linear boundary here, we would end up misclassifying a significant number of samples from both groups. This demonstrates the limitation of a simple model. To accurately classify this new, complex data, our decision boundary must adapt and become more complex. It needs to become curved or nonlinear. Machine learning algorithms are designed to find this optimal, complex boundary that minimizes misclassifications, ensuring the model generalizes well to new, real-world complexity. Moving beyond nonlinear boundaries, we encounter an even more common challenge: data overlap. With even more diverse data, the classes begin to intermingle. They no longer form perfectly separable, distinct clusters. Look at the chart on the left, labeled overlapping data. The red circles and blue squares are mixed in the center, making it impossible to draw any single curve that perfectly separates them without misclassifying a significant portion of the training samples. In this scenario, where absolute certainty is impossible, we shift our focus from predicting a single class with certainty to assigning a probability to each possible class. This transition takes us to the probability space, shown on the right. Instead of sharp lines, we see smooth gradients. The bright red areas represent a high probability of being fertilized, and the bright blue areas represent a high probability of being unfertilized. The purple area in the middle is where the classes overlap, indicating high uncertainty, a roughly equal probability of belonging to either class. This probabilistic approach allows the classifier to provide a nuance, reflecting the inherent ambiguity in the real-world data. Once we have calculated probabilities, we face the crucial final step, converting that probability into a definitive, hard decision. This is where policy, not just mathematics, draws the final line. The location of the decision boundary is no longer fixed purely by the data. It depends critically on our goals and what type of errors we are willing to accept. Consider the two scenarios illustrated here. The goal might be to maximize recall for the fertilized class. This means we want to be absolutely sure we catch every single fertilized egg, even if it means we misclassify a few unfertilized ones. Those are known as false positives. This results in the wide, encompassing boundary shown on the left. Conversely, we might want to maximize precision for the unfertilized class. In this case, it is paramount that every egg we classify as unfertilized is genuinely unfertilized, even if we miss a few of the truly unfertilized ones, accepting false negatives. This results in a tighter, more conservative boundary, as shown on the right. The policy defines the trade-off between maximizing sensitivity, recall, and maximizing accuracy, precision, tailoring the classifier's behavior to the specific business or safety requirements. Up until now, we've focused on binary classification, the simple case of two choices. But the world is often more complex than two choices, and our classification problems must evolve to match that complexity. Imagine our egg sorting problem has evolved. We no longer just care if an egg is fertilized or not. We need to sort it into three distinct qualities. We now have three classes of eggs: winners, which are viable fertilized eggs; yolkers, which are safe unfertilized eggs; and quitters, which are unsafe fertilized eggs that must be discarded immediately. As you can see in the diagram, the data points now form three separate clusters, each requiring its own designated region. Assigning an input sample to one of three or more possible classes is called multiclass classification. Just like in the binary case, the classifier must find a series of decision boundaries that carve up the space into regions corresponding to winners, red, yolkers, blue, and quitters, yellow. This moves us beyond simple yes or no questions to complex, multi-outcome decisions. Solving a multiclass problem directly can be computationally challenging. However, we have elegant ways to solve a complex problem by breaking it down into a series of much simpler questions. One of the primary methods for achieving this is called one versus rest, or OvR. The core idea is simple. For n classes, we build n separate binary classifiers. Each binary classifier answers a single, straightforward question: does this sample belong to class X or not? The diagram here shows 5 classes, A, B, C, D, and E. Instead of building one classifier to distinguish among all 5, we build 5 separate classifiers. The first classifier is trained to separate A from the rest, B, C, D, E. The The second separates B from the rest, and so on. This approach dramatically simplifies the learning task for each individual classifier, transforming one difficult multi-class problem into n easy binary problems. Once trained, these individual classifiers work together to determine the final class. When we want to classify a new sample using the one versus rest approach, we run that single input data point through every binary classifier we built. You can think of each classifier as a spotlight focused on its designated class. As the sample passes through classifier A, it receives a probability score indicating how likely it is to be class A. It then passes through classifier B, classifier C, and so on, receiving a unique probability score for each class. In our example, the input sample is run through all 5 classifiers. The results are tallied in the probability scores bar chart below. Classifier A gives a 10% probability, B gives 15%, C gives 10%, and D gives 20%. Critically, classifier E returns a 90% probability. Because the one versus rest strategy assigns the sample to the class associated with the highest probability, the system confidently classifies the new input, as this streamlined process makes OvR a highly efficient and popular technique for handling multi-class problems. While one versus rest is highly efficient, there is an alternative approach for multi-class problems known as one versus one, or OvO. This method also utilizes binary classifiers, but it builds significantly more of them, resulting in a tournament of duels approach. Instead of comparing one class against all others, OvO builds a separate, specialized classifier for every possible pair of classes. To illustrate, if we have 4 classes, A, B, C, and D, we don't build 4 classifiers, we build 6. Specifically, we need a classifier for a versus B, a vs C, A vs D, B versus C, B versus D, and C versus D. The diagrams on this page show the resulting specialized boundaries for these 6 distinct pairings. Each of these 6 classifiers is only trained on data points belonging to the 2 classes it is tasked with separating, allowing it to become highly optimized and transparent in that specific head-to-head comparison. The key difference here is the increased volume of classifiers needed to cover all potential matchups. The mechanism for making the final decision in the one versus one strategy relies on a voting system, bringing transparency to the classification process. When a new sample is introduced, we run it through all the OvO classifiers. Since each classifier is trained only on 2 classes, it simply votes for one of those 2 classes based on where the new sample lands relative to its specific decision boundary. Let's trace the classification of the central black dot in our example. When run through the A vs B classifier, it votes A. When run through a versus C, it votes A again. However, when run through the B versus D classifier, it votes B. After running the sample through all 7 possible duels, we compile the final tally. In this instance, Class A receives 3 votes, Class C receives 2 votes, Class B receives 1 vote, and Class D receives 1 vote. Since Class A received the maximum number of votes, the sample is classified as A. This voting method provides a clear, step-by-step breakdown of how the sample fared in every head-to-head matchup, offering more explainability than a single probability score. While the voting mechanism of one versus one offers greater clarity and explainable results, this benefit comes at a significant computational cost. The number of binary classifiers required for OvO grows quadratically with the number of classes, n, specifically calculated as n multiplied by n-1 divided by 2. This scaling issue presents a serious limitation for large-scale applications. Look at the graph here, which clearly plots this exponential growth. While classifying 4 classes requires only 6 classifiers, jumping to 10 classes requires 45 classifiers, and increasing further to 20 classes necessitates building 190 classifiers. By the time we reach 30 classes, we need a staggering 435 separate binary models running simultaneously. This massive requirement directly increases the training time, consumes vast amounts of memory, and dramatically boosts the computation needed for every single new prediction. Therefore, despite its transparency, OvO often becomes impractical compared to the linear scaling of one versus rest when dealing with a large number of classes. So far, our entire discussion has revolved around supervised learning, the assumption that our data is perfectly labeled. But what happens if we are dealing with raw, unlabeled data? We might have thousands of data points, but no human has gone through the arduous process of assigning a category or class to them. In such cases, we must pivot from supervised learning to unsupervised learning. Unsupervised learning is the process of automatically finding intrinsic structures, groups, or patterns within the unlabeled data itself. The primary technique used here is called clustering. Clustering algorithms analyze the similarity and proximity of the data points and automatically derive groups. The chart on the left shows the unlabeled data, just a collection of gray points. After processing this through a clustering algorithm, the output on the right, identified clusters, shows 5 distinct groups that the algorithm found autonomously. This allows us to make sense of large datasets without prior human knowledge or labeling effort. One of the most foundational and widely used methods for unsupervised learning is k-means clustering, which finds groups based on the proximity of data points. The algorithm operates by trying to identify a specified number of cluster centers, which we call centroids, and then assigns every data point to the nearest one. Let's walk through the steps. Step 1 shows the raw, unlabeled data. In Step 2, we introduce the initial centroids. These are randomly placed centers, k equals 3 in this example. Step 3 is the assignment phase, where every data point is colored and assigned to the nearest centroid. Crucially, in Step 4, the centroids are updated by moving them to the geometric center, or mean, of the points currently assigned to them. This process iterates until the assignments stabilize. A key detail here is the hyperparameter, k. We, the human operator, must tell the algorithm how many clusters to find before training begins. Choosing this value of k is a critical decision that dictates the algorithm's outcome. The k you choose is not just a technical input. It fundamentally dictates the story the data tells, making the freedom to choose, k, both a blessing and a curse. If we already know the underlying number of groups, we can guide the algorithm perfectly. But if we don't, our initial choice dramatically alters the final clustered outcome. You can see the consequences visualized here. If we pick too few clusters, such as k equals 2, the algorithm is forced to merge 2 or more distinct natural groupings into a single large cluster. Conversely, if we pick too many clusters, for example k equals 7, the algorithm will artificially split naturally coherent groups apart, creating subgroups that may not have any real-world meaning. Choosing the optimal k often requires trial and error, domain knowledge, and external evaluation methods to ensure the resulting clusters accurately reflect the underlying structure of the data and serve the desired analytical purpose. We've explored how complexity forces us to move from linear boundaries to nonlinear ones, and then from certainty to probability. Now we address a final counterintuitive challenge known as the curse of dimensionality. It seems logical that adding more features or dimensions to our data, such as color, texture, or temperature, in addition to weight and length, should provide richer information, thereby improving a classifier's performance. Up to a certain point, this is absolutely true. But beyond that optimal peak, the opposite occurs. Adding more dimensions actually makes classification worse, causing performance to decline dramatically. This graph illustrates the phenomenon perfectly. Classifier performance improves until it hits a maximum, but then the red curve, the curse, takes over. This decrease in performance due to an excess of features is a critical paradox in machine learning, and understanding why it happens is essential. The reason classification performance drops in high dimensions boils down to one fundamental problem: density. To successfully find a reliable decision boundary, a classifier needs a dense concentration of samples within its region of influence. As we increase the number of dimensions, the volume of the space explodes exponentially, and the fixed number of data points we possess becomes incredibly sparse. Imagine a simple one-dimension line. If we place 10 data points along it, the density is high. Now move to 2 dimensions, a square. Placing those same 10 points makes the space feel empty, the density has dropped. In 3 dimensions, a cube, the volume has increased so much that those 10 data points feel almost infinitely separated. The density is critically low. In high-dimensional spaces, Say, 100 features. The data points are so far apart that the classifier cannot reliably find local neighborhoods or boundaries, leading directly to the breakdown of performance. Your data becomes effectively lost in the vastness of the space. While the curse of dimensionality paints a bleak picture of high-dimensional space, what saves us in real-world machine learning is something called the blessing of structure. If data points were spread completely randomly across a 100-dimensional space, classification would indeed be impossible, as predicted by the curse. Fortunately, real-world data is not uniform or random. Instead, it possesses intrinsic structure. Data tends to be clumped together in smaller regions or lie on simpler, lower-dimensional surfaces embedded within the high-dimensional space. Look at the two cubes. The uniform cube shows randomly distributed data, hard to separate. The structured cube shows data clustered around a simpler, two-dimensional plane, the orange slice. This means that even if the space has 100 dimensions, the data itself might only occupy an effective dimensionality of 5 or 6. This blessing means we don't need high data density across the entire voluminous space. We only need high density where the data actually resides, allowing our classifiers to find meaningful boundaries even in vast dimensions. To truly appreciate how strange high-dimensional spaces are, we must abandon our 3D intuition because it fundamentally fails us. Consider the volume of the largest sphere that can fit inside a cube. In a one-dimensional line, the ratio of the sphere, a line segment, to the cube, the whole line, is 1. The sphere takes up the entire space. In 2 dimensions, the square, the inscribed circle already leaves a significant portion of the cube unused, the 4 corners. In 3 dimensions, the sphere leaves even more volume in the corners. As the number of dimensions increases, the sphere's volume relative to the cube's volume plummets toward 0, as clearly demonstrated by the graph. At 10 dimensions, the sphere's volume is virtually 0 compared to the cube. What this means geometrically is that in high dimensions, almost all the volume of the box is concentrated far away from the center, right in the corners. This strange geometry is why distances and boundaries behave so differently when we move beyond 3 dimensions. If the previous slide didn't challenge your intuition enough, consider this paradox. In high dimensions, things can be inside the box and simultaneously appear bigger than the box itself. Imagine packing a spherical orange at the center of a cube, which is protected by spherical balloons placed in each corner. We set the radius of the corner balloons to 1. In 2D and 3D, the central orange is clearly smaller than the box's half-width, radius equals 2. However, as the dimensions increase, the central orange grows relative to the corner balloons. The diagonal distance from the center to the corners increases rapidly. At 4 dimensions, the orange's radius is already larger than the corner balloon radius. But the most counterintuitive point occurs at 9 dimensions. Here, the radius of the central orange becomes equal to the box's half-width. This means the orange is touching the box walls. In all dimensions 10 and higher, the orange is mathematically larger than the box meant to contain it, yet it still fits inside. This illustrates how high dimensions stretch and distort space in ways our 3D minds cannot easily comprehend. We have traveled a journey from drawing simple lines in the sand for binary classification to encountering profound paradoxes in high-dimensional geometry. The overarching lesson from this anatomy of decision-making in machine learning is clear. Intuition is unreliable. You must rely on the math. When dealing with complex algorithms, especially those operating in hundreds or thousands of dimensions, our experience in the 3D world, our 3D intuition, is actively misleading. Concepts like volume, distance, and density simply work in ways we don't expect. Therefore, when building and deploying these systems, we must proceed with extreme caution. We must rigorously monitor performance, trust the logic and mathematics that govern these spaces, and always prefer empirical rigor over gut feelings. The success of modern machine learning hinges not on human intuition, but on the precise power of mathematical rigor.